Hi, my name is Justin Chovanec, and this summer I did research on simulating neutron rotations in magnetic fields. The broader experiment here is being conducted to study the weak interaction between particles and to look for exotic fifth fundamental forces. To study the weak interaction, a polarized beam of cold neutrons is sent through a liquid helium target, and then the beam will have its polarization reversed and be sent through the same target. Since the weak interaction maximally violates parity, the results from the two tests can be subtracted, and this will eliminate any effects due to the strong interaction so that the weak interaction is all that is left. To search for exotic fifth forces, the same basic apparatus is used, except metal plates that run parallel to the beamline are used in place of the liquid helium target. Again, since the neutrons are initially polarized, angle changes from the initial polarization angle will be detected at the end of the beamline. My specific contribution to this experiment was to update any values used in the code to ensure that the simulation was being run at the most current form of the experiment, and to write an algorithm to read in histograms and select statistically relevant data sets from these. Previously, the simulations utilized the Physics Analysis Workstation, or PA, which forced the supercomputer where the simulation was run to link to external libraries, thus slowing the simulation. For small tests, this time difference is negligible, but most tests run using this simulation will involve up to 1 billion neutrons, so the time difference becomes much more drastic. My algorithm reads in histograms, such as the one seen in Figure 1, and then turns these into cumulative distributions, such as the one seen in Figure 2. The cumulative distribution is created by taking each individual bin and making its new value its current value plus the sum of all previous bins. At the end, the bins are divided by the total number of counts, which will normalize the distribution so that all values fall between 0 and 1. This is important because when a new value is needed in the code, a function is called which identifies the proper array where the distribution is stored. Then a random number is selected, which will be between 0 and 1. The function then iterates from the beginning of the distribution until it finds the bin where the random number is just less than the value of that bin. From there, the function takes the midpoint of that bin and the next lower bin to get the midpoint of the midpoint for the new value of the neutron. This is done for things like location within the beamline and wavelength of the neutron. And this is done to get a truly random sample of neutrons to use in the simulation. A beginning to end search is used instead of a binary search because most histograms are weighted more heavily at the beginning, so a front to back search is not much slower and occasionally much faster than a binary search. Here I have two different histograms. The first is data for a wavelength of the neutrons that was collected on the NIST cold neutron beam. And the second is the cumulative distribution created within the code for the histogram seen in Figure 1. Thank you for watching my presentation, and I look forward to answering any questions you have.